So now that we have established that we need a go-to-goal behavior and possibly an avoid obstacle behavior in order to go between points A and B, and we have figured out that if we have a differential drive robot that we can model as a unicycle with constant velocity v0, then what we can really control is the heading. And the way we control it is phi dot is equal to omega. Now, let's define the error. Error equals to phi desired minus phi, so the desired heading minus the heading we're in. And then we can use a PID controller acting on E. And we should remember that we may not want to act directly on E because it's an angle, so this little trick with arctangents 2 will allow us to ensure that E stays between minus pi and pi. Okay, let's use this to actually build a behavior that takes us to a goal. So the question then is the only unknown here, which is what's phi desired? Well, let's say that we're located at x and y. We know where the goal is, x goal and y goal. And the way we know it is either because of the sensor skirt disk abstraction we talked about, or some other way of knowing the goal location. Well, it's not very hard to compute what the desired angle is. It's simply y goal minus y divided by x goal minus x, and then arctangent of that. So phi desired in this case, of course, is this angle here. So that's given by this arctangent formula. So now, all we do is we plug it in to get the error, then we plug the error in to get the controller, and then we hook the controller in to get the update on the heading. Okay, so without further ado, let's do it. Okay, here's my first attempt. Look at this, we're getting there to, what? All right, what just happened here? This was attempt 1, and well, the robot started out looking in the wrong direction, and then it started to turn nicely, maybe not enough, and then something happened. And it seemed to happen roughly when the angle here was close to minus pi over 2, but in fact, this is exactly what happened. The problem here is that I forgot that I was dealing with angles. So the issue is angles. As we talked about, let's not plug in angles right away. Let's always make sure that they are within minus pi and pi. And by the way, omega in this case was just k times the error, so it was a pure p regulator, no I and no d part. But this is what happens even if you do a nice design and you forget that you're dealing with angles instead of other entities. So let's go to attempt 2. Same controller. Now I'm putting omega equal to within quotations here. This simply means that it's not exactly this because I'm doing the arctangent 2 on this. And let's see what the robot is doing. It's spiraling around the star here a little bit. Yeah, not that great, I must say. So what seems to be the matter? Well, the problem is the following. I'm driving the car at a constant speed, v0, and then I'm turning based on this equation up here, and it doesn't seem like I'm turning fast enough. You know, if I'm going really fast, then I need to turn a lot to actually get to where I want. So the problem simply is that I'm not turning quickly enough. Or maybe I should slow down when I get closer to an obstacle. And in truth, if you're controlling v and omega at the same time, you need to be a little bit more, you need to be more smart in your control design than just a PID regulator on the heading error. But since this is what we're doing right now, simply what we should observe is the gain is not high enough. K is not high enough to steer us towards where we would like to go. So let's do the same thing, but let's make K bigger. So this is attempt 3. We're doing the same thing. We have K big. And again, we have the quotations there because it's not exactly this we're doing. What we're really doing is this arctan2 trick on the error on the angles to make sure that we get something between minus pi and pi. And this is just right. This was a successful control design, and in fact, pure P part. And I don't know if you remember this video that I showed you that showed how the metric drift was happening. It was this video.
Okay.
Well,
3,
Let's look at it again. And this time I have the volume on because it's really exciting. This is a competition. And what these robots are doing is exactly what we just saw. Go to goal using a P regulator. And this is a competition of the P games. And in this case, one robot did well and the other one was forced out of bounds. But this was exactly the controller that was running on this kind